Hello, ladies and gentlemen. Welcome back. We are starting Unit 5. Now, Unit 5 is a little longer unit. It's actually 10 lessons, but we're going to do the first 5 lessons and then take a test on that, and then take a test on the last 5 lessons, because 10 of them, that's a lot of lessons before we do an assessment. So this first lesson, ladies and gentlemen, is on interpreting graphs. Graphs of relations and functions provide visual information that can help you understand what is happening. There is a dynamic relationship between a graph and a real-world situation. In this section, you will investigate this relationship. A picture can be worth 1,000 words if you can interpret the picture. Now, this first example is dealing with a Ferris wheel turning round and round. So, ladies and gentlemen, how many of you have ridden on a Ferris wheel? We're going to take a few minutes here and we're going to watch a video on the tallest Ferris wheels in the world. Well, there you go, ladies and gentlemen. Those are the tallest Ferris wheels in the world, and you'll have to go to Singapore to ride the tallest one at 541 feet. All right, so let's take a look at this graph. So we've got this strange looking wavy line. And it says that the x-axis is representing the time that has elapsed in seconds. So what I'm going to go ahead and do, ladies and gentlemen, is I'm going to go ahead and label that time, and that's in seconds. Okay, and then the range, the y value, the height of the seat from the ground in feet. Okay, so I'm just going to put height, but it's the height of the seat that you're sitting in from the ground. Now, we're not going to use the world's tallest Ferris wheel, ladies and gentlemen. So let's just say like the one at the state fair. All right, the state fair, that one is roughly, oh, that one's roughly, I think, 80 feet tall. Okay, that's roughly 80 feet tall. The average Ferris wheel is actually 63 feet. Okay, but the one at the state fair is a little bit taller than that. All right, and so now let's think about this. Okay, time on the Ferris wheel. You know, you got to get on the Ferris wheel and then they finish loading it. And once you finish loading the Ferris wheel, then you're going to spin around a few times. So on the bottom, I'm going to put a 0 here for 0 seconds. You know, that's like the time you get on the Ferris wheel. And then you're riding the Ferris wheel. You're going up, you're going down, you're going up, you're going down. So let's just say, you know, the Ferris wheel ride doesn't last that long. And once you get going, it really only lasts, you know, maybe 3 minutes. Okay, maybe 3 minutes. And 3 minutes, that's about 180 seconds, folks. Okay, and this is in seconds. So what I'm going to do is I'm going to say, okay, I'm going to ride the Ferris wheel for 3 minutes from 0 to 180. That's my domain, ladies and gentlemen. From 0 seconds, and we use this notation, from 0 seconds to 180 seconds, and in the middle we put the letter X because X represents the domain. And we put a less than or equal to in between the number and the letter. Okay, now the range value, well, I'm going to put the Y in the middle because the range value is the Y, okay, the up and down. Now, technically, the range is the height of the seat from the ground. Now, the seat does not hit the ground, folks. If we were in class, I would demonstrate this, and I would sit on the floor, okay? I would get down on the floor, and that's not how you get on a Ferris wheel. The Ferris wheel, the seat is already off the ground, about 2 feet, so you can easily sit down in it. So the range value really should only go from 2 feet, not 0, because you don't get on you don't sit, the seat doesn't touch the ground. And then if this Ferris wheel is 80 feet, okay, we're just going to put an 80 there. Now that can vary, okay, all of these can vary a little bit, but these are reasonable range and domain, okay, and I'm going to label that seconds. All right, so there's example 1, and if you need to, go back and listen to that again and think about it. Remember, you have the power of pause and rewind. All right, let's look at the next one. Number 2, or example 2. What is the real world meaning of this graph, picturing the relationship between the number of people getting haircuts and the amount charged for each haircut? All right, each year I always ask the class, okay, in your opinion, what is too expensive for a haircut? Just a haircut, okay? Nothing else, no extensions, no highlights, just a haircut. What's too expensive? And I always get a wide range of numbers. And most of the time, people say, okay, just a haircut, I will not pay over 40 bucks for a haircut. Okay, so what I'm going to do, ladies and gentlemen, is I'm going to put the 40, I'm going to put 40 bucks right there, and this would be 0 bucks right there, right? That would be the 0. Here, I'll take that off though, because that 0 can mean more than one thing here. And on the y-axis, you see the number of haircuts. So let me read this. The number of haircuts depends on what is charged for each haircut. As the price increases, the number of haircuts decreases linearly. The slope indicates the number of haircuts lost for each dollar increase. The y-intercept represents the haircuts cost that is too expensive for everyone. The y-intercept indicates the number of haircuts when they are free. Okay, well, if you think about, let's just do this in a 1-day period. Okay, 1 day. So this person cuts hair for 8 hours. All right, so what is a reasonable number of haircuts that a person can do in 1 hour, okay? Number of haircuts in 1 hour. Well, you know, it depends upon what's getting done, right? If you get a buzz cut like me, you can go through a whole lot of people in 1 hour. But, you know, on average, it's maybe 3 people on an hour, okay? 3 people per hour. See, now if we were in class, we would have a discussion on this. Well, if that's the case, ladies and gentlemen, and it's an 8-hour day, okay, 3 people per hour. So that means, you know, a person could cut 24, could cut hair for 24 people. Now, we're going to say that if the haircuts are free, they're going to get through 24 people, just haircuts, nothing else. But nobody's going to pay for it if it's over 40 bucks. Okay, 40 bucks is the limit. So our domain, ladies and gentlemen, is $0 and 40 bucks is the maximum. That's our domain value. Okay, again, $40 is what the last 2-3 years that the class has pretty much come up with the same general. I'm not going to spend more than 40 bucks for a haircut. Okay, the range value, so that would be obviously if it's too expensive, nobody's going to get their haircut, so 0. And then if they're free, well, there's going to be a line at the door, and we'll say that that person can cut 24 people's hair in 1 day, which is an 8-hour day. Again, we're just going 1 day, 8 hours, 3 people per hour. All right, let's keep rolling, ladies and gentlemen. Let's look at the next one. Okay, this one is just a little story that's already done for you. So, which of these graph pictures a student walking speed from the time she realizes she might be tardy for class until she arrives at class? Well, the solution's already given to you here, all right? So graph B is probably the best answer, okay? So this is probably the best answer. Okay, so the student realizes that they're late, so they pick up speed, they get faster and faster, and then when they get to class, okay, well, once they get up to speed, okay, once they get to their speed, how fast they can go in the hallway, then they maintain that speed until they get to class. Okay, so graph B is the best answer. Now, graph A is not a good answer because it is unlikely that anyone can instantly get up to speed and maintain that exact speed. Okay, so A is out. C indicates she knows she will be late and has given up trying to beat the clock. Notice, however, that her speed isn't 0. Okay. All right, again, don't forget, if I go too fast, pause and rewind if you need to. All right, let's keep going here. Next example. Sketching a graph of the following. Okay, so here we're gonna have to think about the graph. So this is the situation. We've got a kettle of boiling water cools in a warm kitchen. Okay, well, folks, boiling water is 212 degrees Fahrenheit. Okay, if we were in class, I'd have you look that up. So 212 degrees Fahrenheit. And we're going to go ahead and put 0 here. Well, we know it's not going to get below freezing, right, ladies and gentlemen? Okay, so now it's a warm kitchen. Okay, well, it's going to cool, but it doesn't cool linearly. It doesn't cool at a consistent rate. It cools kind of like this, ladies and gentlemen. It cools and it curves, okay, until it reaches the room temperature. Now, room temperature depends, you know, most of the time room temperature is about 70 degrees Fahrenheit. Okay, and then the bottom, this is the time that it takes to cool. Well, we're going to go ahead and put that in minutes. Okay, so boiling water, you turn it off, you let it cool to room temperature. Well, from 0 minutes to how many minutes do you think it will cool? Well, if it's boiling water and you're going to cool it to room temperature, that takes a little bit of time. It takes roughly 30 minutes, maybe longer, okay? But 30 minutes is reasonable. So that's your domain, from 0 minutes to 30 minutes. The range, well, now, the water is not 0 degrees, okay? Now, when you do this, ladies and gentlemen, you still have to put the big number on the right side. The big number always has to be on the right side. The small number always has to be on the left side. Now, the room temperature, ladies and gentlemen, is about 70 degrees. Okay, you might put 75, you might put 68, you might put 65. Okay, some people have their houses set different. During the day, I have my house set at 70. And at night, I let it cool down to about 62. It's a lot easier to sleep. I like it. I like it cooler when I sleep. So I'm gonna put 70 degrees right here. So that's the range value, 70 degrees to 212 degrees. Okay, think about that. So that is a kettle of boiling water that's cooling in the kitchen. All right, let's look at another one. Sketch a graph of the following situation. All right. You blow up a balloon. Okay, ladies and gentlemen, we're going to watch this guy blow up a balloon. All right, get ready.
Lifehacker reader Izzy's Anime says, I can't blow up a balloon. I remember others trying to teach me, just can't make it happen for some reason. Izzy, let's figure this out together. I'm going to teach you how to blow up a balloon. First, take the balloon, stretch it a bit. This way, when you blow it up, it's already primed to stretch out. Now, put the open end in your mouth, not past your teeth, just past your lips, and keep your tongue out of the way. At first, the balloon will only inflate a little bit, so you need a big burst of air to start expanding the rubber. Then it gets easier. Keep one hand on the spout by your mouth, and the other, if you want, on the back of the balloon for control. If you need more air, use one hand by your mouth to pinch the balloon shut. Keep going as long as you can feel it growing, but stop when you feel it only getting tighter. Now, you're ready to tie it. Stretch the long skinny part where you are blowing. It's okay, it's not as tight as the rest. Loop it around your index and middle finger, then under your fingers, and through. And that's it. Now you're ready for a birthday party, or a baby shower, or a funeral that's in very poor taste.
All right, wasn't that exciting, ladies and gentlemen? All right, so now we're going to sketch the situation of blowing up a balloon. But then, you know, we have many things here that we can do for, like, the X value, the X axis. So what I have chosen to do here is how many breaths does it take to fill up the balloon, okay? So I'm going to label that number of breaths. All right, and then on the side, how big does the balloon get? Now I'm going to measure the diameter, okay, the distance through the balloon. So I'm going to put diameter here. And I'm going to measure that in inches, okay? Now, if we wanted to measure, we could do the volume, okay, how much air is in the balloon, but it's a little easier to think about how wide that balloon is, the diameter. All right, so some possible domain values. Well, again, you're going to start with 0 because you haven't blown any air into it yet. Okay, and then you're blowing the balloon up. And I would say, you know, on average, you should be able to blow up a balloon in 5 to 6 breaths. Okay, depending upon how big it is. So we're just going to put, 5 as our maximum. We're just going to use 5, folks, 5. 5 is our maximum number of breath, excuse me, breaths to blow it up. All right, the range, the diameter, well, let's just do, a normal balloon, that's probably, about as wide as a ruler. So we're just going to say 12 inches. There's some really small balloons, but let's just say 12 inches. Okay, so we've got our range and domain figured out. But now what is it going to look like? Okay, now let's think about this. So I'm going to start right here where there's no air in it yet. You haven't put any breaths in it and it hasn't expanded. So then I'm going to go ahead and I'm going to blow air in it. Okay, you ready? Here's the first breath. Okay, it stops. You're not letting any air out. You blow again. All right, and you blow again. And then you blow again. And then again, until you get to where it's at that tension. Well, then the balloon is going to stay there until either you pop it or days later it loses air and it gets smaller again. Okay, so that is kind of what that graph looks like. Interesting, huh? Okay, it's a straight line because you're blowing air in it and then you're pinching it shut. You're not losing air. At least I hope you're not if you're doing it like that guy just showed us. All right, let's keep rolling here, folks. Let's look at this next one. All right, so in this one, okay, this one's already done for you. And I'm going to make this a little smaller so that we can see the graph as I'm reading it, okay? I'll read the first paragraph and then I can move it and you can see it a little bit better. So students at Columbia Heights High School have complained that the soft drink machine is empty too often. Student council members have decided to study this problem. First, they recorded information and made a graph showing the number of cans in the soda machine at various times during a typical day. There, the graph gives them a lot of information about the use of the soda machine. All right, so here is what the graph looks like. Okay, can't quite see the whole thing. So I'm just going to generalize it here, folks. Instead of reading this up here, okay, instead of reading what this says, you can pause it and read it. That would be a good idea. All right, so we see that the school cafeteria doesn't open until 7 a.m. All right, so at 7 a.m., ladies and gentlemen, we see, I'm going to go ahead and make this bigger. So at 7 a.m., we see that the pop machine, the soda machine, is full. Okay, then students come into the school, right? Students come into the school from 7 o'clock to 8 o'clock and they're buying soda. So it goes down. Okay, well, class gets started. Students are going into class. But then, from 9 o'clock, 8 o'clock to roughly 10:30, it slows down a little bit. They're still buying soda, but it slows down. Probably in between classes, they're buying soda, but not as many students, and they're not buying it as fast. Well, you'll notice that at roughly, what is that? Roughly 10:30, ladies and gentlemen, it looks like the person came in that fills those machines, fills it back up again. Okay, and then students are in class for a while, but then guess what? Look what happens, ladies and gentlemen. It must be lunchtime. Look. That must not be a very good big pop machine, must not hold very much. Those students, they buy all of the pop and they actually empty it during lunch. Wow. Okay, then the person comes back and then quickly fills it up again, right? Well, not completely full, okay? Only filled it up part way. Almost full, but not completely full. Okay, and then the students, well, they've had their fill of pop for the day, but some students are still buying some pop during the day, probably between classes. And then look what happens. At the end of school, must be school's over with, that soda machine runs out again. Oh my goodness, they must be making some good money on this pop machine, man. Okay, you'll notice there's a little bit of break in there. And then, look, at 4 o'clock, that person comes back again. They must be making good money on this pop machine. They fill it up again, and then from a little after 4 o'clock to, about 7 o'clock, it goes back down again. Probably because there's after-school activities. Okay, so think about what I just said. Rewind and listen to that again if you didn't quite catch all of those. But that's kind of what that graph, at least that's what I think it's showing me. All right, and I think that's pretty close to what this paragraph is saying here. All right. All right, one more, and then we're going to do a bunch of this stuff during class. So hopefully it'll be really easy. All right, so our last one, this is an invent a story. All right, so we see that we have a graph with time at the bottom and water level. So the graph at the right tells a story. It could be a story about a lake, a bathtub, or whatever your imagination can create. All right, so here's the little story that came with this graph when I found it. It is a dark and stormy night. The cold bucket stood empty in the yard before the torrents of rain came. As day broke on the horizon, the rain subsided. The bucket stood quietly through the morning until old dog Trey arrived, as thirsty as a dog. The sun shone brightly through the afternoon when Billy, the kid next door, arrived. He noticed two plugs in the side of the bucket, one of them about a quarter of the way up, and the second one was near the bottom. As fast as you can blink an eye, he pulled out the plugs and quickly ran away. So obviously the bucket, as it rained, the bucket got full, got more water in it, and it got fuller. Okay, and then it leveled off when the rain stopped, and then the dog drank some, but then Billy came by and unplugged it, and it drained really quick. All right, ladies and gentlemen, that's what we're looking at. We're looking at interpreting graphs and figuring out, well, what's a reasonable domain and range value for that scenario. We're going to practice more of this, ladies and gentlemen, with our classwork. See you soon.